Slide 1. In the name of Allah, the most gracious, the most merciful. Slide 2. The latest and most advanced state of artificial intelligence to date. Slide 3. The return of neural networks. After 1986, with the introduction and development of the backpropagation algorithm, neural networks, especially multilayer neural networks, regained scientific attention. These algorithms, based on the chain rule in differential calculus, enabled error propagation from the output layer to previous layers, thereby optimizing network weights during training. Development of neural networks after 1986. Multilayer neural networks, after resolving issues present in older models like single-layer perceptrons, multilayer networks, with at least one hidden layer, gained the ability to solve nonlinear problems. The universal approximation theorem, proven by Sebenko in 1989 and Hornick in 1991, demonstrated that multilayer neural networks with just one hidden layer can approximate any continuous function. Approximation means reaching the closest value or function in the input data. Recurrent neural networks, RNNs, developed in the 1980s for processing sequential data such as natural language and speech. RNNs faced limitations due to the vanishing gradient problem, which hindered long-term learning. In 1997, Hochreiter and Schmid-Huber introduced long short-term memory, LSTM, largely addressing this issue. In subsequent decades, RNNs improved significantly and were widely used in natural language processing and machine translation. Convolutional neural networks, CNNs, initially introduced in 1989 by Jan LeCun, CNNs were used for handwriting recognition in the 1990s. However, their major success came with AlexNet in 2012, developed by Kraszewski et al., which revolutionized performance in the ImageNet competition. Using convolutional filters for feature extraction from images, CNNs became highly effective in applications such as computer vision, object detection, and medical image analysis. Reinforcement learning, initially developed independently of neural networks, reinforcement learning merged with deep neural networks in the 2010s. This led to the introduction of models like DeepQ-Network, DQN, in 2015, which utilized neural networks to solve decision-making problems in complex environments such as video games, robotics, and financial trading. Current status, up to 2025. Neural networks have reached unprecedented levels of advancement and play a key role in various fields. Massive neural models. The advent of more powerful computing and vast datasets has led to the development of large-scale language models like GPT-4 and Llama. Based on the transformer architecture, these models have extensive applications in natural language processing, machine translation, and text content generation. Multimodal neural network development, networks capable of processing multimodal data, images, audio, text, are now used in products such as smart assistants, autonomous vehicles, and recommendation systems. Advanced medical applications. Neural networks have made remarkable progress in disease diagnosis, medical image analysis, and drug design. For instance, models based on CNNs and transformers perform at expert levels in radiology and pathology analysis. Current challenges of neural networks. Need for high-quality data. Neural networks require large amounts of labeled data for optimal performance. Interpretability. A major issue is the lack of transparency in how decisions are made. High energy consumption. Training complex neural models demands significant computational power, leading to high energy usage. Security and robustness. Neural networks can be vulnerable to adversarial attacks. Future trends. Lightweight and energy-efficient models. Lightweight neural networks for deployment on mobile devices and IoT systems. Transfer learning. Leveraging pre-trained models to reduce the need for large datasets. Integration with traditional AI methods, combining neural networks with fuzzy logic, evolutionary algorithms, and expert systems. Slide 4. Probabilistic reasoning and machine learning. Probabilistic reasoning uses principles of probability theory to make decisions under uncertainty. This method enables the estimation of event probabilities based on observed data. Machine learning involves developing algorithms that learn from data and are used for automated prediction or decision-making. The combination of these two fields has led to the creation of models that not only learn from data but also manage uncertainty effectively. Developments since 1987. 1987 to 1995, introduction of Bayesian networks for modeling probabilistic dependencies between variables. These networks were widely used in disease diagnosis and financial risk management. 1996 to 2005, development of probabilistic graphical models such as Markov models and the expectation maximization algorithm for parameter learning. During this period, latent Dirichlet allocation, LDA, was introduced for topic analysis in texts. 2006 to 2015, integration of probabilistic models with deep learning techniques, leading to models like variational autoencoders, VAEs, and Bayesian deep learning. These models enabled the generation of new data and better uncertainty management. Current applications. Medicine, use of Bayesian neural networks for disease diagnosis, treatment response prediction, and personalized medicine. Business, use of probabilistic graphical models and Bayesian inference for customer behavior analysis, personalized recommendations, and market trend prediction. Robotics, use of probabilistic reinforcement learning and partially observable Markov decision processes, POMPs, for training robots in complex and uncertain environments. Challenges. Uncertainty management, modeling and reducing uncertainty in large and complex datasets remains a significant challenge. Interpretability, many probabilistic machine learning models are difficult to interpret, reducing the transparency of their decisions. Computational efficiency, probabilistic reasoning methods often incur high computational costs, especially with high-dimensional data. Sparse data, managing incomplete or rare data continues to be a persistent challenge. Future directions. Neurosymbolic models, combining neural networks with probabilistic models to enhance reasoning and decision-making capabilities. Social reasoning, developing models to predict human behavior in social and economic contexts using probabilistic theories. Autonomous AI, utilizing probabilistic models in self-driving systems, independent decision-making, and recommendation engines. Advanced predictive models, leveraging Bayesian deep learning and Markov logic networks for more accurate predictions in high uncertainty conditions. Slide 5. Big data. Big data refers to a collection of data that cannot be managed using conventional data processing methods due to its large volume, high speed of production, and variety of data types. This data is collected from various sources such as social networks, videos, photos, sensor information, and commercial data. The goal of using big data is to extract useful information for better decision-making and process optimization. 5 V's in big data: volume, the amount of data available; velocity, the speed at which data is generated and processed; variety, different types of data, structured, semi-structured, and unstructured; veracity, the quality and accuracy of data; value, the ability to extract useful information from data. Developments. The developments in big data have accelerated significantly in recent years. Before 2000, the start of collecting structured data using Oracle and IBM relational databases. 2000 to 2010, the emergence of Hadoop and MapReduce for distributed processing of large data. 2010 to 2020, the development of Spark for faster processing, the introduction of NoSQL for managing unstructured data, and the extensive role of artificial intelligence and machine learning in data analysis. 2020 onwards, the emergence of edge computing for local data processing, blockchain for data security, AI-based data analysis and AutoML, and quantum computing as the future of large data processing. Slide 6. Current status. Today, big data is used in various industries such as e-commerce, healthcare, taxation, transportation, and even urban planning. Companies like Google, Amazon, and Facebook use big data to personalize services, analyze customer behavior, and optimize performance. Currently, advanced tools like Apache Kafka for managing streaming data and Apache Flink for real-time processing, as well as deep learning for analyzing complex data, are available. Additionally, the importance of data security and legal issues related to privacy in big data is increasingly recognized. Challenges. Data management. Managing large volumes of data has become a major challenge. Privacy and security. Protecting sensitive information and preventing unauthorized access to data is one of the most important challenges. Lack of specialists. There is still a need for specialists who can correctly analyze data. Costs. Implementing big data projects can be costly, especially in the initial stage. Unstructured data. Analyzing unstructured data, such as text, images, and videos, remains a challenge. Technologies such as natural language processing, NLP, and computer vision are advancing to analyze this type of data. Future. The future of big data will be accompanied by the advancement of new technologies. In the future, it is expected that AI and deep learning will play a greater role in data analysis and significantly improve how additional data is used. Edge computing will grow, processing data at the point of production, like IoT devices, instead of cloud processing. Real-time data. The use of streaming data for immediate decision-making will increase. Blockchain will likely play an important role in data management and creating trust in big data networks. Smart cities. The use of big data in managing cities to optimize transportation, energy, and urban services will expand. As technology continues to advance, big data will become one of the most important tools for global economic and scientific development. Thank you very much for your time. I hope I have been able to make a small contribution to AI education.